So in order to do calculus of vector valued functions, we need a notion of a limit. And we're going to define that in class, and we're going to be very careful about how we do it. And from there, we'll be able to build up to some of our calculus objects. But I went ahead and gave you the definition of a limit here. So we're going to say that, as long as we've got some function r of t, a vector valued function defined around some maybe problematic t value or just some t value in our domain that we want to analyze in terms of limits, then we're going to say that the limit of that vector valued function as t approaches t naught is some new vector L if, and then here's this statement that you saw in a Calc 1 class. It's very similar to that. So this is the epsilon delta proof that you were given in a Calc 1 class. And all of this first part should look very, very similar. The difference is over here, we've got the difference between r of t and what we're claiming the limit of the vector valued function is. That's some statement given in terms of limits, and we need to make that less than epsilon. So don't worry about this. We will study this in class. But I want to go ahead and give a visual interpretation of what we mean by that. And the first thing I think we need to say about this is that up above in the previous video I said, hey, we can define limits as long as we can define a notion of length. But the thing is here is for this function, which is mapping, from, let me write it this way, sorry, which is mapping from R to R3, the notion of length in R is different from the notion of length in R3. So over here, this is the traditional absolute value, which measures distance from the origin on the real number line. So here we have, here's the real number line, here's the, t, and maybe here's t naught. So we want the distance between t and t naught to be less than some value delta. That's very different than what we mean by the difference between two vectors, and then we take the magnitude of them. So this absolute value here is a magnitude, referring to the length of the given vector. And if the magnitude of a vector is approaching some very, very small number, it's essentially we're saying if the limit exists, we can make the magnitude as small as we want. What we're saying then is that the difference between these two vectors would have to be approaching the zero vector, but we decide that we're approaching the zero vector by saying that the magnitude of it can be made arbitrarily small. So here I've got a fairly crude picture that I want to take a look at. And to just give you kind of a quick overview of limits, and what I tried to do here was I tried to put a hole in this graph of this vector valued function here. And that's traditionally, when you first start studying limits, you want to use limits to explore holes in graphs. It's kind of our first introduction to them. And so what we see here is you would expect that if we were to bring if we were to plug in t values into this vector valued function, we would get vectors that are getting closer and closer to, and we could do that from either direction of t. Those t values are getting closer and closer to some t equals t naught, so, but they're not quite there. And what we would say, careful, I just deleted that. And what we'd like to claim is that the limit as t approaches t naught of this function r of t is this red vector that I've sketched here, vector L. That's what we'd like to claim, is that red vector, not that hole there, but the red vector that's been drawn, but up pointing to that hole. We would like to say that the limit as t approaches t naught of r of t is this new vector L, and we do so sort of by studying the behavior for t values near t naught. And so we would say as the t values get closer and closer to t naught, it appears that the blue vectors that I'm sketching are getting closer and closer to that red vector. But what do I mean by closer and closer? And when I'm talking about vectors getting closer and closer together, what I mean is that the difference between the two vectors has to have a magnitude that's approaching 0. And that's something that we'll explore further in the classroom. So let's continue on down. So we're going to say that the limit as t approaches t naught of some vector valued function is this vector L, provided, and another way of saying that is the limit as t approaches t naught of the magnitude of r of t minus L needs to approach the number 0. So this is magnitude here, and this is the number 0. The length of the difference between those two vectors needs to approach 0 as t approaches t naught. So that's just another way of describing what I just depicted in the picture above. And again, we'll explore that in class. So please, if you're struggling with that, don't worry about it. But there's a big result that we're going to see, and that big result is if we've got a vector value function, in this case I did it in R3, then as long as these three limits all exist, if you could take the limit of the individual component functions as t approaches t naught, as long as each of those limits exist, then the limit as t approaches t naught of r of t, that limit that we're trying to find here, is simply the limit as t approaches t naught of the first component function, the limit as t approaches t naught of the second component function, and the limit as t approaches t naught of the third component function. And that's a big result. That's a huge result for us. Why? Because as soon as we get that big result, we're able to bring over all of the stuff that we did in Calculus 1. That won't happen for all of the types of functions that we extend calculus to in this class. It'll be far more complicated to do, but this particular task then is relatively easy. So, why is this a big result? It says that computing derivatives of a vector valued function simply requires taking the derivatives of each of the coordinate functions. And in fact, computing the indefinite integral of a vector valued function simply involves computing the antiderivatives of all of those coordinate functions, and computing the definite integral of a vector valued function simply requires taking this can be done simply using the single variable fundamental theorem of calculus result. And so that's what I mean by all those results carry over. So in the next video, we'll go ahead and do limits, and we'll do calculus with these vectored valued functions. Please know, though, that while we're doing that, we're taking on assumption a couple of the statements that I made up here, specifically this big result. If we don't have this big result, then you cannot do the stuff that we're going to do in the next video. But I'll see you there. Let me know if you have any questions.